What if I told you that the easiest way to build giant black holes in the early universe was dark matter?
That's impossible!
I know, it's probably wrong, but it's a very cool idea and I could not resist talking about it. Here's the setup for the problem. We are seeing constantly, with every year that passes, we are seeing more and more giant black holes appearing when the universe was very, very young. The current record holder is called UHZ1, which I affectionately call the Uzi one. Uzi one is a galaxy that was alive when our universe was less than 500 million years old. So very, very, not like total first generation of stars and galaxies, but like right after that. And it's not any galaxy, it's a quasar. It's super bright, one of the brightest sources of emission electromagnetic radiation in the entire universe are these quasars. A single quasar will outshine like 1 million galaxies at once and shine for 10 million years at once. Like, these things are insane. They are powered by supermassive black holes. Matter falls in towards a supermassive black hole, compresses, heats up, emits a bunch of light, and we see it as a quasar. Now, the thing with Uzi 1 is that its black hole is around 40 million solar masses. There's a large uncertainty, that's a very rough estimate, but no matter what, we're talking tens of millions of solar masses. This thing is a beast. It's a supermassive black hole. It's like 10 times bigger than the supermassive black hole in the Milky Way. Now, here's the problem. Not just Uzi 1, but all of its friends. We're having this massive problem in understanding how we can get such giant black holes to appear so early in the history of the universe. That's because we know of exactly one confirmed way to make black holes, and that's through the deaths of massive stars. If you take a giant star and let it go supernova, go boom, boom, it makes a black hole in its core. Now, this black hole will be 5 solar masses, 10 solar masses, maybe 20 solar masses on the top end. It's not going to be big at all. Now, black holes can grow. They can merge together, they can accrete material, they can suck up, vacuum up material in their surroundings, and they can get bigger and bigger and bigger. But these processes take time. Black holes need time to find each other and merge. Black holes are limited in how quickly they can accrete material because the material that falls in heats up, pours out a bunch of light, prevents other material from falling in. This is called the Eddington limit, and it limits how quickly a black hole can eat. If you look at a giant black hole living when the universe is, 400 to 500 million years old after the Big Bang, there's only so much time from the appearance of the very first stars, which we think occurred somewhere in the 1 to 200 million year range. But even in the most optimistic scenarios where you're making the first stars as early as possible, they die as quickly as possible, they make the biggest possible black hole, and then they grow at that Eddington limit, you're just not getting 40 million solar masses in a few 100 million years. It just doesn't work. The math just doesn't add up. It's a very interesting and intriguing problem.
Houston, we have a problem.
One way around this is to start your black holes bigger. If they can get started bigger, then they can just grow and merge at the usual rate and reach supermassive status in time. Now, this would mean a different way of forming black holes. One way is through direct collapse. If you take a giant gas cloud and just let it compress and compress and compress, and then skip the whole star formation bit and just create a black hole in its core, maybe you can get a black hole that's, say, 10,000 solar masses. And if you do that early enough, then it can grow, it can merge and accrete and become something like Uzi 1. The trick here is that you have to keep it warm. If the gas cloud cools off too rapidly, then it will fragment. And then these fragments, these pieces will collapse on their own. And instead of having one giant monolithic collapse into a giant black hole at the center, instead you get thousands of stars, which is bad. Okay, so to keep a gas cloud warm, you have to prevent it from cooling. And what cools off a gas cloud are the presence of heavy elements, like anything heavier than helium. These are called metals in astronomy. Don't ask me why, weird term, but we're stuck with it. Thankfully, in the early universe, there aren't any metals because there are hardly any stars to produce the heavy elements, so check. But another thing that can cool off these giant gas clouds is when hydrogen bonds together to form molecular hydrogen. And molecular hydrogen can emit a lot of radiation, act as a heat sink, cool off these gas clouds, make them fragment, make them turn into a bunch of stars. So how do you prevent the hydrogen from bonding together? You do that through UV radiation. If there's enough UV radiation, it will break apart the molecular hydrogen, keep it atomic, keep it nice and warm, and boom, you can get this giant collapse. So we're a few steps down the line here, folks. How do you make UV radiation if there aren't a lot of stars? The answer in this paper is dark matter. I know, it sounds weird, but here's the idea. There's a hypothetical form of dark matter that is ultralight. This is related to theories of the axion and its relatives. This ultralight dark matter has two key properties. One, it acts more like a wave than a particle at galactic scales. You can actually think of it as like interstellar sized quantum waves, which is super fun, which means you can get regions where the waves crash together, where they condense together, where you can get real strong amplification of the dark matter, where you get a whole bunch of this axion-like dark matter in one spot. And ultralight dark matter can convert into radiation. So the idea behind this paper is that maybe if you take one of these collapsing gas clouds of hydrogen, maybe there's a lot of dark matter that goes along with it, and the dark matter converts into photons, converts into infrared radiation, but then there's a lot of turbulence in the cloud that energizes it, that scales it up to UV radiation, which breaks apart the diatomic hydrogen, which keeps everything nice and warm, and the whole cloud collapses at once to form a giant black hole of 10,000 solar masses. And then fast forward 100 or 200 million years, and boom, you get supermassive black holes in time. Now that's a stretch. There's a lot of links in that chain that have to go right for this story to be right, which is why it's probably wrong, but this is a very interesting problem in the early universe. We need creative solutions. Our traditional solutions, the straightforward stories of galactic evolution, star formation, black hole formation and evolution, aren't cutting it. Something happened in the early universe to generate these giant black holes that is not operating today. Conditions were different. Cosmos was young then, was willing to take some risks that's a little too old to take on now. Maybe it involved dark matter. Maybe not. But we need creative ideas because we need to generate ideas. We need to generate observable tests that we can go after with something like the James Webb Space Telescope to see if there's a way to distinguish these models, if like the rate of star formation changes or the size of stars changes or the population, the kind of light they're emitting. Maybe this ultralight dark matter will emit a radiation in a particular way that we can pick up. We need to start testing these ideas so that we can cross some out, elevate others, and hone in on a solution. That's why I'm always a big fan of creative, probably wrong ideas, because that's how we make progress.